In this lesson, we're going to find the area enclosed by one loop of the three-leaved rows r equals cosine 3 theta. So the first thing we'll remember is our formula for the area, which says the area is the integral from a to b of 1/2 r squared, so 1/2 cosine squared 3 theta d theta. So our key is to figure out the bounds of integration a and b. So we need to figure out the bounds of integration a to b that will produce one loop of our curve. So the first thing I'll notice is that our loops correspond to coming into the origin. The origin means that r is equal to 0, so I'm going to set r equal to 0. That gives us cosine 3 theta is equal to 0. Cosine is equal to 0 when the inside, in this case 3 theta, is equal to pi over 2, or 3 pi over 2, or 5 pi over 2, 7 pi over 2, etc. So cosine is equal to 0 at the odd multiples of pi over 2, which gives us, so 3 theta equals these values, which gives us theta equals pi over 6, 3 pi over 6, or pi over 2, 5 pi over 6, 7 pi over 6, 9 pi over 6, etc. So we need to figure out what pair of values is going to give us one loop of our curve. So the first thing I might do, there are multiple options at this point, the first thing I might do is let's just look at this first pair, pi over 6 and pi over 2, and see what happens. So I know I'm going to do my table of values, so theta, and then my r, which is cosine of 3 theta. So I know that when theta is pi over 6, r is cosine of pi over 2, so 0. And similarly, when theta is pi over 2, again, r is 0. So that's how we found those values. I might now think, let's take a value in between pi over 6 and pi over 2. So I'm going to take, for example, pi over 3. I then get cosine of pi, which is minus 1. So when my angle is pi over 3, so my 60-degree mark, so when my angle is pi over 3, my radius is negative 1. So instead of pi over 3, 1, I'm flipping to the other side, so I get out here, which tells me I go from when theta is pi over 6, I'm at 0, and then I'm coming out to minus 1 and back into 0. So this one is my pi over 6 to pi over 2 loop, which tells me that for my area now, I can say integral pi over 6 to pi over 2, 1/2 cosine squared 3 theta d theta. There are many other ways to get the area. One way would be to say when you know theta is 0, cosine 0 is 1, so this point corresponds to theta is 0, r is equal to 1. Pi over 6 is in at 0. Graph your curve cosine 3x. You'll see that this gives you 0 to pi over 6. So you could do twice the integral from 0 to pi over 6. So there are multiple options here for finding the area of this curve. You could alternatively do any of the other loops, so you could do this loop, for example. So as an exercise, a good idea would be to go through and figure out what bounds correspond to your different loops. But let's go ahead with the pi over 6 to pi over 2 bounds and figure out how to compute our area. So the first thing I'm going to do is pull out the 1/2, and also I'll get integral pi over 6 to pi over 2 cosine squared 3 theta. Now, anytime I'm integrating cosine squared or sine squared, I'm going to need to use my angle identities. So I'm going to use the identity cosine squared x is 1/2 1 plus cosine 2x. We don't need it here, but I'll write it down. Sine squared x is 1/2 1 minus cosine 2x. And if you need to use these on a quiz or a test, I will give you these formulas. So using that, so I have my 1/2 pulled out, and then I get integral pi over 6 to pi over 2. Cosine squared 3 theta, so I have my identity with a 3 theta in place of x, so I'm going to get 1/2 1 plus cosine 6 theta d theta. I'll pull that 1/2 out, so now I have a 1/4 in front and do my integration. Integral of 1 is just theta. Integral of cosine 6 theta gives me 1/6 sine 6 theta. And I'm evaluating from pi over 6 to pi over 2. So plugging in my bounds now, I get 1/4 times, so pi over 2 plus 1/6 sine 6 pi over 2 gives me sine of 3 pi, and then I subtract off my lower bound, so pi over 6 plus 1/6 sine 6 pi over 6 is just sine of pi. Sine of pi I know is 0, so that term goes away. Sine of 3 pi is 0, so that term goes away. And I end up with 1/4 times pi over 2 minus pi over 6. And this gives me pi over 12, which is approximately 0.62. So now we might go back up and say, well, does 0.62 make sense? Our radius was 1, so the entire circle would have a radius of an area of pi r squared, or pi, so definitely we should be much less than pi. We should also, it seems, be less than 0.75 because we're less than a quarter of the circle. A quarter of the circle would be pi over 4, so about 0.75. So an area of 0.62 does make sense in terms of our actual figure. Again, as an exercise, it would be useful to go in and see what other bounds you could have used. So to get the entire first loop, we said you could do 2 times 0 to pi over 6, or you could do the integral from 5 pi over 6 to 7 pi over 6, so that would give you the first loop. To get the second loop, you could do the integral from pi over 2 to 5 pi over 6. There are many other ways to do this using symmetry, so to do, as we said at the beginning, half of a loop and then multiply by 2, so make sure you understand the various ways to compute this area. The key of this lesson was using these angle identities to actually work out the integral, and again, if you need one of these for a quiz or a test, I will give you these identities.